Right, suppose we want to check for the validity of an argument. And an argument is a set of statements in which some are the premises, called P1 and P2, and then one is the conclusion. You could have an argument with more than two premises, but let's consider just a simple case. So suppose we have as premise number one, P implies Q or R, and as premise number two, not Q and not R, and as conclusion, not P. The question is this a valid argument or not? Now I'm going to write here the definition of a valid argument. So a valid argument is an argument such that whenever all the premises are true, the conclusion is also true. So that's our definition of valid argument. Whenever all the premises are true, the conclusion is also true. So we need to check all the situation in which all the premises are true and check whether the conclusion is also true. If there are some situation in which all the premises are true and the conclusion is false, that makes the argument invalid. Okay, so let's start by listing our premises right here on top. So P implies Q or R. So we have our premises here, P or R, and then our other premise, not Q and not R, and then our conclusion, not P. So this is our premise number one, premise number two, and then our conclusion. And what we need to check is whether, in all the cases in which both these premises are true, what happens to our conclusion? Is it true or not? Now, before we get to that, however, we need to proceed with simpler steps, and namely, we need to look at the atomic formulas that occur in our premises and conclusion. And there are three such atomic formulas, and I'm going to list them. I'm going to list them here. So we have P, we have Q, and we have R. So these are our three atomic formulas. There are no other atomic formulas here to consider. And what we need to do is to consider all the possible combination of truth value that we can give to our three atomic formulas. And there are going to be 8 possible combinations since we have 3. There are 2 at the power of 3, namely 8 possible combinations. So one quick way to list all the combinations is the following. So we write 1, 1, 1, 1, so a series of 4, 1, and then 0, 0, 0, 0 for P. Then we write 1, 1, 0, 0, 1, 1, 0, 0, that's for Q. And then 1, 0, 1, 0, 1, 0, 1, 0 for R. And this gives us all the possible combinations. So we can draw our lines here, trying to keep everything relatively neat and organized as much as we can. Okay, so we have all the combination for our atomic. Then we can move one step more complex. So we can consider Q or R. So we have Q or R right here. Now Q or R, so we consider here Q and R here. So Since both Q and R in this first possibility have value 1, so this gets value 1. In these other cases, either Q has value 1 or R has value 1, so Q or R also gets value 1. Then we have, this case is different because both Q and R has value 0, so Q and R should have value 0. These are the three cases. We have 1 again, and then we have a 0. This is just by the truth table of the or the disjunction. Now let's consider not Q and not R. So not Q and not R. Now not Q is relatively easy. We just need to flip the truth value of Q. So we have 0, 0, 1, 1, 0, 0, 1, 1. So we are flipping the truth value of Q. And for not R, we are flipping the truth value of R. So we have 0, 1, 0, 1, 0, 1, 0, 1. Okay. So we are done with not Q and not R, and now we can finally determine the truth value of our premises here. So we have P1, so let's start with P1, and we can start here with looking at our P. So we have P gets value 1, and then Q or R get value 1, so this will have value 1. P has value 1, and then Q and R has value 1, so this gets value 1 again. Also, P has value 1 and Q has value 1, so it gets value 1 again. Here is a case in which P has value 1, but Q or R has value 0, so this whole thing will have value 0. Now, in all the remaining cases, what's interesting is that P always gets value 0. So that's easy. We can just write 1, 1, 1, 1. Because whenever the antecedent here gets value 0, the whole implication will get value 1. Okay, now we can move to not Q and not R. This is our premise 2. And we see that in the first combination, both of them has value 0, so their conjunction will have value 0. In the next two cases, one of them has value 0, so the conjunction will also have value 0. This is a case instead in which both have value 1, so the whole conjunction will have value 1. Then we have value 0, 0, and 0, because you see that they both have value 0, at least one of them has value 0. And then finally value 1, because both of them here have value 1. Okay, we are ready finally to look at not P. And this is simple. We just need to look at the truth value for P. And so if we go back here to the truth value for P, we see that it has 1, 1, 1, 1, 0, 0, 0, 0. So when it comes to not P, we just need to flip the truth value of P. So we have 0, 0, 0, 0, 1, 1, 1, 1. Okay. Now we are finally able to go back to our definition of a valid argument. So if you remember, a valid argument is an argument that whenever the premises are all true, whenever all the premises are true, the conclusion is also true. So that's our definition of a valid argument. Now we need to check whether our argument here with these two premises and the conclusion satisfies that definition. So what are the situations in which all the premises are true? Well, not this first situation, not the second one, none of the situation except the last one right here. So this is a situation in which both the premises are true. And if both the premises are true here, we need to check what about the conclusion. And we see that this conclusion is also true. So indeed, we can go back to our definition of a valid argument. Whenever all the premises are true, the conclusion is also true. And this definition is indeed satisfied here because whenever all the premises are true, the conclusion is also true. So we can say that this is a valid argument. And we are done.